Hi guys, welcome to today's lesson. So today we're going to be looking at circles and angles, right? So we're still under Euclidean geometry, or if you like, they normally call it circle geometry as well, right? So we're still talking about that, but now we started with looking at circles and lines and looked at what exactly is it that is a relationship between the lines in a circle. Now we're going to look at what is the relationship between the angles now in a circle, right? So that's what we're going to try and talk about. So let's just jump right into it. So remember our mind map or our concept map is we've looked at the concept of a radius and the concept of a chord, right? A tangent we're going to look at a later stage. And then we also looked at the concept of perpendicular lines, right? So now we're looking at the concept of angles, and we're going to try and talk about an angle, maybe at the center, same segment, and alternate segment. Now, have you ever thought about, remember, we're still looking at how do I construct a right angle using only a compass, a ruler, and a pencil. But to do that, we're going to talk about an investigation. Remember, the concept of a chord is from one point of the circle, of the circumference, to the other point of the circumference. And then in terms of a segment, this chord that I have here, right? Let me use a different color so you can see. So this chord that I have here, it normally cuts this into two segments, which is this segment that I have here, right? And this other segment on this side, this segment here. So the chord normally cuts the circle into two segments, but we're going to look at that at a later stage in the very same lesson. So part of a circle is we have what we call a semicircle. Remember, semi means half. So half a circle, we normally find half a circle because of a diameter, right? So remember, a diameter, one of the definitions of a diameter is, yes, it is twice the radius of the circle, but the actual diameter is, it is a line that cuts the circle into two equal parts or into two halves, right? And those halves, we then call them semicircles. We don't really call them a half circle, no, it's a semicircle. Now, a chord, as I just said, it normally cuts the circle into two segments. Segment 1 and segment 2, or vice versa, segment 2 and segment 1. But now we have specific words or names that we give these segments. The smaller one, we call it the minor segment, and the bigger one, we normally call it the major segment. So if maybe I try and draw another one here, if I draw it like this, this will be the minor segment, and this one will be the major segment, right? So that's what we are talking about, minor and major. That's what you need to think about. At a later stage, you will see why these segments are all important, because we're going to be talking about angles in the same segment. What exactly does that mean? It means they're on the same circumference on one side of the segment based on the chord. And this is where also you will be thinking about what I said last time, that at times when I give you a chord, I won't give you the actual line. I will just give you points on the circumference, right, which would then depict a chord. We have what we call a sector. You know, it's a part of the circumference of the circle. Also, an arc will be an arc will be also a curvy part on the circumference as well. Subtend actually means form, right? So if I have something like this, and I have A, B, and C, the angle at B, we say it is subtended by AC, right? Meaning it is formed by AC. So if I say it's angle ABC like this, it means that this point and that point are what subtends this angle here, or sometimes we write the angle like this with that sign there. Also, it means the same thing, that A and C subtend the angle at A. So you please need to note that. Now, remember, a sector will be this area that I have here of the circle, and then you still remember what radius is about, from the center to the circumference of the circle, right? Then the arc, right? So the chord will be this one here. That's a chord. But now the minor segment, right? The circumference part of the minor segment, we then call it an arc. Think at some point when you guys were doing constructions, then they said draw an arc, and you would do something like this, right? That's what an arc is about. Arc will be like a line, but a line that is curving, not a straight line as we normally say. And then a major arc and a minor arc, that's what we normally talk about as well. Remember, major, bigger one, minor, smaller one. But now, also we have what we call the angle at the center. The angle at the center will be the angle that is formed by the minor arc, or formed by the minor segment. And then we have the angle at the circumference, which is the one that is in the major arc or the major segment. But now look at what is happening. They are both formed or subtended by the very same arc that I have here, right? So from the arc to the center, from the arc to the circumference, right? That's the condition. And you will see why this is important at a later stage. The investigation we have is when 2 points on an arc subtend an angle at the center and an angle at the circle or circumference, is there a relationship between these? So I said when I started, we're going to try and look at the relationship between angles in a circle, right? So if from my arc to the center, from my arc to the circumference, same points, what is the relationship of those two angles that I have there? Is there even a relationship for that matter? That's what we're going to be trying to do. And remember, we're going to be using an investigation. I'm going to be showing it with my pen, but you can try and find this at a later stage and move it as the instructions are going to be saying to you to try and do that. Now, you can see that here, if this angle is 105 and that angle is 52, there is really no relationship between the two at the moment. You will then move the point B along the circle until it gets closer to point A, and then back towards C, right? While moving this, I want you to pay attention to AOC and ABC. AOC will be this angle here, and ABC will be that angle there. So they said, move B along the circle until it gets close to point A, right? So you move this until it gets to point A here, and then you move it to C as well. So what that means is move A closer to C, then move point B along the circle until it gets closer to A, and then back towards C. Still pay attention to those angles. This will look something like this. So you can see now, I kind of now have this angle being twice that angle, right? 36 times 2 is 72. So look at that and try and see exactly what is the point there. If I move this point here, right? So move this point that side and also move it that side, and try and look at what is the relationship that you are getting with that angle AOC and the angle ABC. Also move point A away from C closer to B. While moving it, observe the very same things that we are talking about. So let me just erase on this thing so I can show you. So here they're saying move A away from C closer to point B, right? You move A away from C but closer to B, that side. So if I then put it to be here, my point A, and I have that angle there, and I have this angle there, what will be the relationship of this angle here with that angle? Will it still have this same relationship that we are seeing right now, where one is half of the other? That's what you need to try and figure out with that. Also, if you look at moving those points again, another way of looking at this will be if I have this angle here, right, and that angle there, they also seem to have a 1:2 relationship or 2:1 relationship. You need to think about that as well. What exactly does it mean? What happens when I move the points around? When I move the point C that way, what happens to this angle here? And what happens to that angle there? That's what you need to think about. If I move this one that side, what happens to this angle here? And what happens to that angle there? That's what I want you guys to please be thinking about when trying to solve this. So make sure that you try this investigation, move those points around, try them, and look at what exactly is it that it will do for you. What do you observe? What do you see? And what conclusion can you then draw? Can this lead us to a theorem? We will then see after the ad break. Let's just go quickly to an ad break and I'll be back with some more. Stay tuned. Hi guys, welcome back. So the first thing that I want you to try and see is what is the relationship between an angle at the center and an angle at the circumference, right? Provided though that they are subtended by the very same arc or the same chord, right? Remember I said an arc is normally when there's a chord there, but we normally don't really draw the chord. Hence I've been saying to you that times if I just give you 2 points on the circumference, it means that there is a chord there. So just try and think about that. Now we're going to try and look at what happens then when you actually do move it around. Does the relationship that we've been seeing where it's twice one another or something like that, does it still stay the same or not? What happens when you move it maybe to the top there? What happens to the angles? Do they still have a relationship or they don't have a relationship whatsoever? And then we'll pin it down to an actual theorem to try and see exactly what does this mean. So let's just have a look at it quickly. So remember we've looked at a radius, a chord, and then now we are busy with the concept of the angles, and specifically we're looking at the angle at the center, right? And about the same segment or the alternate segment. The summary of the observation is the very first conjuncture was when 2 points on an arc or a chord subtend, remember subtend form, an angle at the center and an angle at the circumference or at the circle, then the angle at the center is normally twice or double the size of the angle at the circumference of the circle or at the circle, right? So what does that mean? It means if I have a nature like this, this must be my O, which is the center, and I have that there. And let me just draw that properly. So I have something like this. This angle here will be 2x, and that angle there will be x, provided that they are subtended by the same arc, which is this part down there. Now, when 2 points on a diameter subtend an angle at a semicircle, then the angle is what? Is 90 degrees. So what does this mean? It means that, remember we said twice the angle at the circumference. So this angle is 180 degrees. It means the angle that this arc here subtends as well, but now on the circumference of the circle, it must be half of this, because we said they have a relationship of 2:1. Then this becomes a 90-degree angle that I have there. Right? So the theorem is the angle subtended by an arc at the center of a circle is normally double the size of the angle subtended by the very same arc, but at the circumference. And remember, as mathematicians, we have short ways of writing these things. Angle is normally that greater than kind of symbol at center is equals to 2 times angle at the circumference, if you were to use this theorem. Also, the reason why I have the reason there, it sounds like I'm saying reason a lot, but really, the purpose of me putting the reason there is that whenever you use this theorem, you don't prove the theorem. Remember with the first lesson we had, we said because the theorem is already there, you don't prove it again. Instead, you use that theorem to try and just use it as a statement, because you know that 1, there's a center, 2, the angle at that center is subtended by the same arc as the angle at the circumference, then there will be a 2:1 relationship. So at times I will give you one angle at the center and I say find the one at the circumference. You'll just have this one. Your reason will be as what you are seeing on the board, that angle at the center 2 times angle at the circumference. So you don't necessarily need to prove the theorem itself. You can just use it as a theorem because it has already been proven for you. Now, the angle subtended by the diameter is at the circumference of the circle is 90 degrees. We normally say the angle it's an angle, not really angles, let's just say one angle in a semicircle, right? So this will be an angle in a semicircle. So what exactly is the converse of the statement that I have here? The angle subtended by the diameter or the center at the circumference of the circle is 90 degrees. So I want you to take a moment and think about that, right? What is it? So you know that if the angle is subtended by the diameter and the angle is 90 degrees, it means that if the angle is 90 degrees at the circumference, then it is subtended by the diameter. So that's what the converse is about. So if an angle is subtended by a chord at the circumference of the circle is 90, then the chord is a diameter. You see, and then my reason will be converse angles, angle in a semicircle. Don't really say angles because then it makes it seem like there's a lot of them, though it's normally 2 on opposite sides of the circumference. But for now, we're looking at just 1. And then we need to look at the relationship between these angles that I have here. So this angle here and that angle there, what is the relationship between the two? You need to think about that, right? But the condition that you are seeing here is they are subtended by the same chord, right? Are subtended by the same chord. Does that make them equal? Does that make them to have 1:2 relationship? Or does that make them not to even have any relationship for that matter? You need to think about that. But let's just see exactly what do I mean. So we need to try and prove this particular thing here. So to prove it, I'm firstly going to make it that there is a center here, right? And if there is a center, that's what I have there. So I will then say, remember I said with a formal proof, you need to know what you are given, right? And this will be, let's mark it O. So this will be circle, center O, and then we have those angles that we have there. Our construction here will then be draw radius OR and OU, right? Now, what do we know from this? I'm just going to say proof, right? We don't really know what is the required to prove as yet. We are just trying to see what is actually going to be the relationship based on these two things that I have here. I know that my ROU will be equals to 2 times T, right? Which is actually 2 times beta. Same thing, my ROU again will still be 2 times angle S, which is equals to 2 times angle alpha, right? And the reason is the same for both of these two statements that I've made here. Will be angle at center twice the angle at the circumference, right? Angle at center 2 times angle at circumference, right? Now, what does this mean? Since both of them are ROU, it means that 2T and 2S are actually going to be equal to each other. So this will make it to be 2 beta is equals to 2 alpha, making it, or the reason then being, let me just erase this, not equals to there. And the reason for this will actually be the fact that they are both equal to ROU, and then you know that beta will be equals to alpha. So what does this mean? Remember I said that this is the same segment, right? And that's another segment that I have there. So it means that angles on the same segment but subtended by the same chord or subtended by the same arc are equal to each other. So that's what you need to note about this particular theorem that I have on the board here. So the theorem is angles subtended by the chord of a circle on the same side of the chord are equal to each other. And our reason is normally angles in the same segment. So what am I saying? If I have an angle there subtended by that and an angle there subtended by that, I don't even need to draw a chord there. This angle and that angle there are going to be equal to each other. Why? Because they are subtended by the chord of the circle and they are on the same side of the chord, right? So if my chord was there, they are both on that side of the chord. So then they will be equal to each other. We normally call this angles in the same segment. Why? Because remember that this is classified as a segment. So we need to please remember that. So that's what we have in terms of the concept of angles, right? Remember we said an angle at the center is always twice the angle at the circumference. What is the condition? Provided it is subtended by the same arc or by the same chord. 2, an angle that is subtended by the diameter of the circle on the circumference is always 90 degrees. Converse is if an angle is 90 degrees and is subtended by the chord, then that chord is actually a diameter, right? And then you know that you can try and prove that using the angle at the center is twice the angle at the circumference. The other thing will be the angles that are on the same segment are equal to each other. What is the condition? In everything that I've said so far, the condition is the same. They must all be subtended by the same chord or by the same arc. Then they will be equal to each other. I hope that clarifies a few things for you, and then you can then see the bigger picture of all of this in terms of angles at the center and the angles on the circumference of the circle, and the issue of the chord subtending those particular angles. For now, let's quickly go to an ad break, and we'll be back for the last segment where we're going to try and solve a few questions to try and put this into some context. I'll be back with some more. Stay tuned. Hi guys, welcome back to the last segment of our lesson. So we've been looking at an investigation 1. We then spoke about the theorems where the investigation was actually taking us, right? And those are 3 theorems. Angle at the center is twice the angle at the circumference. 2, an angle that is subtended by the diameter on the circumference is 90 degrees. And 3, angles on the same segment are equal to each other. Now we're going to try and show this in terms of a diagram and try to see how do I then solve the questions that have to do with this, right? But prior to that, I want to show you there's 3 ways that you can see this concept of an angle at the center being twice the angle at the circumference. And you need to really know all 3 of them, because it's not always that you're just going to see the one that it's from the chord to the center, from the chord to the circumference. At times it is a bit fuzzy, but I know that you will know what to do when you see that. So let's just have a look at it. So I'm just gonna go here. So remember that the main one that I said would be when I have something like this, right? That's the main theorem. This is 2x and that's x, right? But also, this can also be given to us as something like this, right? And this is 2x and that is x. And the reason why these 2 are one and the same thing, remember the investigation said that you must move this point that side, right? So if you move it until you leave it here, you did not change the angles. The angles are still there and they still have the same relationship. And then the last representation of this is normally when you have an angle like this, center there. Okay, just assume that this is my center here. It's not really drawn to scale. This angle here will be 2x and that angle there will be x, right? So what am I saying? It means I'll be moving this point up until it gets to somewhere here, right? So you know that this angle here will be 180 minus 360 minus that, which will also be twice that. So these are the 3 representations I need you to please think about. Why I'm bringing this up is because the questions we're going to be solving, not all of them show this theorem as this first one that I have here. At times it looks like that, or at times it looks like the C there. Now, the question is, P, Q, R, B, and A are points on the circle, or with center O, right? Give reasons why. 1, the angle P, which is this angle, is equals to the angle Q and is equals to the angle R, right? Remember, what did we say? This will be angles on same segment, right? So you please need to think about that. It will be angles on same segment. Also, why is PBQ? So PBQ, I have PBQ Q. So this angle here, let me just use a different color so we can see the differences. This one here, PBQ, is equals to PAQ. PAQ will be this one there. So you can see also they are both subtended by that PQ there. So it will still be the very same reason as what I have up there. And then the last one is QAR and QBR. Let me maybe use this color here. QAR, which will be this angle here. And they say this is equals to QBR. QBR will be that one there. You can see also they are subtended by this chord there. So you can see it's not always just going to be straight away that it's up there like this, right? And you have your circle like that. No, at times it might happen that it's an angle here and an angle there. You just need to look at where the chord is, right? And whether that chord is the one subtending both those angles that we are talking about there. So let me go back to that. So the reason why that is the case, what did we say the reason is? This is angles on same segment, right? Segment is normally SEG. You don't really need to write it in full. Similarly with this one, it's the same. Angles on same segment. And then lastly, even with this one, angle QAR and QBR. So if the first letter and the last letter, maybe this is how you can see it as well. And the first letter and the last letter there are also the same, right? It means that the angle in between those two letters is the same throughout, right? And those two letters, these two letters here, they form an arc or a chord, and those two letters form an arc or a chord. So angles on same segment. And then let's look at maybe a question that has values now, where we need to find some values. O is the center of the circle. Remember, you don't assume. I need to tell you that it is the center. Because I said to you last time, monkey see, monkey do does not apply here. Because it looks like it is the center. It does not make it the center. I need to vividly and clearly state for you that O is the center. Or I can say circle center O, or circle O. If I say circle O, it means O is the center. We normally use O most of the time to represent the center, because it's like the origin. So O, origin, right? But you need to be told that it is the center. So please note that. And then passing through the points M, N, P, and Q. And then PON, which is the angle, PON at the center is equals to 109 degrees, right? Now we need to calculate the size of the following angles. 1 and 2, you need to give reasons, by the way. M1, you need to give reasons. And M2, you need to give reasons. So let's do that together. So to calculate the size of N2, right? So I will say in triangle PON, right? PO is equals to ON. And my reason for this is radii, right? And then I know that it means that angle N2 is equals to angle P2. And my reason, in an isosceles triangle, the base angles are equal, right? But that's not what we say. So I will say angles opposite equal sides. And then from there, I can then say that I have 109 degrees plus N2 plus P2 is equals to 180 degrees. You know the reason for this will be sum of angles in a triangle, right? Therefore, this makes my N2 plus, but I'm just gonna let me make it just 1 N2 because that's what we are trying to find. Because it is equal to P2. I will say 2N2 is equals to 180 minus 109, which will then be 71. And then from there, you divide by 2, it makes my N1, my N2 to be equals to that divide by 2 will be 35.5 degrees. And that will be the angle there. And that's what you will then need to do there. So firstly, this is a radii. They are equal. It makes it an isosceles triangle. So this is equals to that. And then from there, because it's an isosceles, it makes the base angles to be equal. But please, 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 let me just tell you this. Don't use the word isosceles nature of a triangle or base angle. That doesn't exist in Euclidean geometry at this moment. You say angles opposite equal sides. That's why those angles are equal. And then you can then start calculating using the 180 degrees. The size of M1, so I know that N2 is 31.5 degrees. 35, I mean, right? So to find M1, right? M1, you can see that this chord here, or this arc here, is what subtends this angle here, right? And the very same chord is what also subtends the angle M1. You see, so you do need to use your highlighters, guys, to see what I'm saying right now. So what will you say? You will just say M1 is equals to 35.5 degrees, which is equals to N2. And my reason for this will be angles on same segment. And you'll be done with that. And then to find M2, I need a reason for that as well. To find M2, you can see that this arc here, right, subtends that angle at the center. It also subtends that angle on the circumference. Angle at the center and angle at the circumference, they have a relationship of 1:2, right? So it means that M2 will be equals to 1/2 NOP, right? And my reason for this will be angle at, I will just do this for center, equal 2 times angle at circumference. And then from there you can then solve for your M2. M2 is equals to 1/2 into 109 degrees, and this is going to then be half of 109 will then be 54.5 degrees. Yes, I think that will be 54.5 degrees. And that's what you will then need to do to solve that. At the last point here, you don't need a reason, guys, because why? It's just basic algebra and using your calculator to do that. So our summary is circle and angle theorems will be, we have an angle at the center, which is twice the angle at the circumference. The angle in a semicircle is 90 degrees, and also it's converse. And then lastly, the angles in the same segment is what you need to look at. So far we've looked at my radius, the concept of a chord and what it is about, the concept of perpendicular lines there, right angles, we know that, the angle at the center we've looked at, same segment, and also the concept of alternate segment means other segment. We're going to link this to the concept of tangents in our next lessons. I hope that is clear, guys. The theorems that I've looked at so far, angle at the center being twice the angle at the circumference, angle in a semicircle, and angles in the same segment. Please note those. And then you then need to know how to also at times prove those particular theorems as formal proofs. But if you are using them, you don't need to prove them. You just need to state them. And I've shown you what is the short version of how do you say angle at the center twice angle at the circumference, or angle that is subtended by a diameter, or angles that are on the same segment. Guys, as I keep on saying to you, mathematics is food for the soul. I will see you guys next time.